Yes, great. Hi, Maura. Let me
Hey there, can you hear me okay?
Yes, I can. Thank you very
Okay,
much.
great.
Excellent. So let me find where we are here. Okay, great. So for the next session, we have Maura McLaughlin, who's going to tell us all about physics with NANOGrav. Maura, just to remind you, I'm going to give it, after 25 minutes, I'm going to give you a 5-minute warning for this 30 plus 35 minutes question. Okay, thank you.
Okay, great. Let me share my screen. Okay. Yeah, first, thank you so much for inviting me to talk to you all. This is my first time at this conference, and I'm really excited to talk to a kind of different group of people and to attend some of the talks. It looks really, really fantastic. So I'm going to talk to you about the work of the NANOGrav collaboration. We are a physics frontier center, and we've been in existence for about 16 years now. We've been a PFC since March 2015, and we've been just renewed for another 5 years, which is really good news for us. And we're very happy to have new members and participants at our meetings. So if you hear stuff that's interesting to you, if you're a student, even if you're a faculty member, and you want to get involved in our work, please let me know. You can go to our website at nanograv.org and find out more about us. These are the logos of all the institutions that are part of NANOGrav at the moment. And I'm going to start just by giving like a super big picture overview of the big science case that we are trying to address. Okay, so if you look back at galaxies that were formed in the earliest stages of the universe, these galaxies are small and they're very disordered. And we know that with time, galaxies grow to be larger and more ordered. And it's generally accepted that this is through a process of hierarchical galaxy formation, right? Where galaxies grow through the mergers of smaller galaxies. And there are lots of questions about the astrophysical processes that bring these galaxies together to form larger galaxies. Now, when we're out in regimes like this, we can actually study galaxies coming together electromagnetically. We can clearly see that these two galaxies are in the process of a merger. But the most interesting astrophysics is happening here, where these two black holes at the cores of these merging galaxies are separated, say, by sub-parsec separations, sub-light year separations, and have orbital periods of only years. Clearly, it would be impossible to look at this galaxy electromagnetically and know that it was the product of a merger. With NANOGrav, what we want to do, though, is use gravitational waves to study the black holes at the core of this galaxy merger and understand the astrophysical processes that are bringing them together. So we're going to do that using gravitational waves. I don't think I need too much of an introduction to gravitational waves for this audience. They're ripples in space-time. They're produced by GR. Here's two black holes that are orbiting each other. Gravitational waves are produced from this system. They travel away at the speed of light. They're carrying energy away, which of course will eventually lead to these black holes merging. Gravitational wave detection experiments depend on measuring changes in proper distance between objects due to passing gravitational waves. So in this little cartoon, if a gravitational wave passed through the screen, this ring of test particles would move like this, right? So the distances between the objects in this ring would change in this quadrupolar fashion. There are two polarizations. This doesn't really matter too much for the purposes of this talk. I'll be talking a lot about strains in this talk. And so the gravitational wave strain is just the change in original path length over the path length. Well, the change in path length over the original path length. And you're all probably familiar with this from LIGO, but a single binary system will have a strain profile with time that looks like this. That's a sinusoid. Okay, so of course, this methodology is what was used to make the LIGO detections. I'm sure you've all heard of LIGO. Just to remind you, here's a picture of it. This resulted in the 2017 Nobel Prize. LIGO, of course, has done an amazing job at detecting compact object mergers. So mergers of black holes and neutron stars with stellar masses, with masses, a little bit more than the sun, up to a little bit more than 100 times that of the sun. So these are our stellar compact object mergers. What we are trying to do with NANOGrav is very analogous. We are also searching for changes in path length between objects. However, instead of using 4-kilometer long arms, we have arms that are thousands of light years long. Instead of test masses that are 40 kilograms, we have test masses that weigh more than the sun. So our experiment is a pulsar timing array experiment. It looks kind of like this. we are monitoring an array of pulsars distributed across the sky and looking for very small perturbations in the arrival times of pulses due to passing gravitational waves. And so this is possible because pulsars are extremely regular rotators. I can't give a pulsar talk without showing one little pulsar movie. And even though this movie is very simple, this is a rotating neutron star. The neutron star has a north and south magnetic pole. Radio emission is produced along these beamed north and south magnetic field lines. So pulsars look like radio lighthouses, right? And the reason that this experiment works is because they're phenomenally precise and predictable rotators. And our experiment is an array because we're looking for changes in arrival times, not just from one of these pulsars, but we're looking for correlated changes in the arrival times of an array of pulsars distributed across the sky. Okay. The particular pulsars that we use for our experiment are called millisecond pulsars. As you might imagine, these are pulsars with very short millisecond periods. There's a few hundred of them in our galaxy. There are many, many more that are detectable with big enough radio telescopes. So our experiment could grow a lot if we have bigger telescopes. About 100 of these 300 so millisecond pulsars are currently being timed for pulsar timing array purposes. There's a whole bunch that just are too messy, are too far away, are in binary systems with eclipses and things like this. But about 100 of them are very high precision timers. This plot here is an ATOP diagram of the galaxy. This is the galactic plane. These are the north and south galactic poles. And all of these dots are millisecond pulsars. The red ones are the ones that we're timing for PTAs. And the point of showing this is just to show that these millisecond pulsars are a generally isotropic population. They're very nearby and they're very old. So they look pretty isotropic. And this is a really nice property for gravitational wave detection. And just a tiny bit about these millisecond pulsars. These are the objects down here in what we call our period versus period derivative diagram. So this is the spin period of all of the pulsars known. There's a dot for each pulsar. They range from milliseconds up to tens of seconds. This is period derivative, or the rate of change of that period. All these pulsars are slowing down with time due to loss of energy from magnetic dipole radiation. These red stars down here are the millisecond pulsars. So they have very short periods and very small period derivatives. And this makes them extremely stable rotators. These guys were formed through the process of recycling. So they were in a binary system. They lived a good life as a normal pulsar. And then when their companion evolved, it spun them up to very, very short millisecond periods. So most of them have white dwarf star companions because of this process of recycling that gave them these ultra short periods. They're kind of like zombie stars. Okay, let me talk a little bit about our experiment and how it works. So we are a pulsar timing experiment. What that means is we observe neutron stars with radio telescopes. These telescopes have, some radio receiver tuned to a particular frequency. We have to do a couple things to our signal before we can measure precise arrival times. We need to de-disperse it. And this just means correcting for frequency-dependent delays through the interstellar medium due to free electrons in the ISM. And we also need to fold the signal so we don't do any measurements on individual pulses, like you might imagine from that simple cartoon. We have to add up a whole bunch of pulses, one on top of another at the spin period of the pulsar to get a very high signal to noise pulse profile. So at each epoch that we observe a pulsar, we will measure a profile like this. So this is kind of like the shape of the pulsar emission beam. And we measure the time of arrival of a pulse at every epoch of observation. Of course, we have a very accurate atomic clock at our radio observatory. And so these TOAs, these times of arrival, are what we do our experiment with. There's the currency of pulsar timing. Now, this is pretty complicated because a lot of things affect the arrival times of these pulses aside from gravitational waves, right? Gravitational waves are the very smallest effect on the arrival time, the smallest known effect, at least, on our pulses. And so we need to do a lot of work to tease out the gravitational wave signature. We need to correct for all the other things that might be happening in our pulsar system. So of course, we need to fit for a rotation period derivative. Most of our objects are in binary systems. And so this binary motion is going to produce Doppler shifts on the pulsar period. We need to fit for that. The signals are traveling through the interstellar medium. We need to fit for what we call a dispersion measure, this frequency dependent delay. Everything's changing with time. The pulsars are moving, we're moving, the ISM is moving. This is going to vary with time. So we need to fit this in a time dependent way. The Earth is going around the sun. That gives us sensitivity to position. We can also measure the proper motion of the pulsar. We're sensitive to parallax. And we even have some effects due to the solar electron density. We'll see higher dispersion measures when our line of sight passes close to the sun. So we have a timing model that accounts for all of these things. And these models look something like this. This is for one particular millisecond pulsar. I'm not going to go through all of this in any amount of detail, but it just shows you kind of an example of the stuff we're fitting for. So spin down parameters, frequencies and rates, astrometric parameters, binary parameters, and we have to worry about the evolution of these profiles with radio frequency, which is an intrinsic effect. And so we have to fit for that as well. And just as an example of the accuracy for this particular pulsar, we measure the spin frequency to be 218.8118438547250 hertz. And we really do know that down to that very last digit. So we can time these pulsars with an awful lot of precision. This pulsar is in a binary with an orbital period of 67.82512992228 days. So this is what these timing models look like. These are the timing residuals for the pulsar that I just showed in this model. And so by residuals, we mean the differences between when our model predicts a pulse at a particular epoch should arrive and when that pulse actually arrived. And by pulse, I mean this integrated profile, not just a single pulse. And so we subtract these two things. This word barycentric is very important. We need to correct these times of arrival to the solar system barycenter, right? So remove those solar system effects. We fit this model, we subtract the two. So if we're doing a good job, right, of modeling everything that's happening in this pulsar system, these residuals are going to be roughly around zero. The error bars should generally encompass zero. So this is a plot for about 20 years of timing on a pulsar with about a 5 millisecond spin period. The units of this are in microseconds. So you can see that these residuals are generally hugging this zero line. The root mean square for this particular pulsar is about 70 nanoseconds over these 2 decades of timing. And so that's pretty good for a 5 millisecond period. This is basically the state of the art in pulsar timing. I don't have time to go into all these different colors too much, but there are different telescope back-end combinations. All of them but the blue and the red points are from the Arecibo Observatory in Puerto Rico. And you can see that the error bars have gotten smaller and smaller and smaller with time. And the reason for that is just better radio instrumentation, better dedispersion and wider radio bandwidths. You can also see that these Arecibo points have way smaller error bars than the Green Bank points. And that's just because Arecibo was a much larger telescope. So collecting area really matters for us. Okay, so let me leave the pulsar overview part behind and talk a little bit about gravitational waves. And then I will tell you about the most recent results from our NANOGrav experiment. So here's the standard little cartoon that shows what our experiment is doing. We have 2 black holes orbiting each other. Here's our telescope. And if you think about 2 pulsars that are sitting in the warped space-time due to the gravitational waves emitted from these black holes, you can see that the path lengths are going to change, right, due to these gravitational waves. And the path lengths are going to be different. They're going to change in a different way for pulsar 1 and pulsar 2, depending on the angle between the gravitational wave source, the pulsar, and the telescope. So just like LIGO, this gives us some directionality to gravitational wave signatures. We're sensitive to much, much smaller frequencies than LIGO. And the reason for that is that we can only detect gravitational waves at the very highest frequencies would be 1 over the cadence of our observations. So if we observe a pulsar every few weeks, something like 10 to the minus 6 hertz, and the shortest, the smallest frequencies we can detect are going to be like 1 over our total time span, right? So if we observe for years to decades, that's like nanohertz. So that gives us the general frequency range that we're sensitive to. If you want to get at the strains that we're sensitive to, you can think about the induced residual due to a gravitational wave. And that's going to be proportional to the strain over the frequency, right? And there's going to be 2 terms to this perturbation. I don't have time to go into this in any detail at all, but we need to worry about the perturbation at the pulsar at the time that radio signal was emitted and at the Earth at the time it was received. So this is a little bit different to the LIGO experiment. And so if we flip this little equation here around, right, we can ask, what are the strains that we're going to be sensitive to? And we can say it's going to be roughly the precisions to which we can time these pulsars over the total time span of our experiment. So if we time a pulsar to precisions of, say, a couple hundred nanoseconds, and this is about average over about a decade, that's like 10 to the minus 15. That's roughly the strains we're sensitive to. So that gives you like a nice ballpark. And one thing I just want to point out is that our gravitational wave wavelengths are much smaller than the distances to our pulsars. So we have like many gravitational wave wavelengths in between the pulsar and the telescope. And this is different than LIGO, right? Where like the whole arms of the detector are getting stretched and squeezed. And this leads to this pulsar and Earth term mathematics. So let's just step back and look at NANOGrav with respect to other gravitational wave detectors. So this is characteristic strain versus gravitational wave frequency. And of course, LIGO is sensitive to frequencies of hundreds of hertz, very short duration signals. And we're sitting way down here in this part of the gravitational wave spectrum. So we're very complementary to LIGO and LISA. We're sensitive only to much more massive objects than these detectors. Our sensitivity curve looks something like this. As we get down to these super low frequencies, we're just not sensitive to them. We would fit them out because these correspond to timescales that are longer than our experiment. We're just seeing the effects of white noise up at these high frequencies. We're not sensitive to periods of a year or frequencies of 1 over a year. And this is because we would fit this stuff out when we fit for the positions and proper motion of our pulsars, because these are yearly perturbations in our residuals. Okay, so let's talk a little bit about the systems that we hope to detect. So there's a lot of electromagnetic evidence for merging galaxies and for black holes at the cores of galaxies. So we know that these systems are out there. We know there must be many of these, very massive black holes with the separations and orbital periods that we're sensitive to. You can look at the strain of these systems. Obviously, it's going to be more for more massive systems. It's going to be more for systems with higher frequencies, for closer systems. Let's not worry too much about this Q. This is mass ratio between the two. One important thing, though, which will come back in a couple slides, is that these objects with the higher strains obviously merge much more rapidly. And this is going to be important when we talk about the stochastic background. So we can look for single systems like this in our residuals, and they would generally look like a sine wave. We call these continuous wave sources. Our systems are not complex. We expect them to mostly be in circular orbits and non-evolving over the time span of our observations. So our templates are way more simple than LIGO templates. This would just look like non-evolving sine waves in our timing residuals. And we're also sensitive to burst sources. So a single event, like a single merger or a close pass of two supermassive binary systems, this would look more like a step function in our residuals. So we both search for both these kind of signatures in our timing residuals. What we think we're going to detect first, and you can see this if you just look at this number here, this is 10 to the minus 17 for a 10 to the 8 solar mass binary with a frequency of a year. And that's a pretty small strain compared to our 10 to the minus 15 sort of characteristic strain we derived on the other slide. So that's pretty hard, not impossible. We think we're going to do it soon, but we think the first thing we'll detect will actually be a stochastic background. So this is red noise, so low frequency noise, due to the superposition of all the gravitational waves emitted from all the supermassive black hole binaries in the universe. We expect this to have roughly a power law spectrum. We expect it to be red. Under the most simple assumptions, we expect this index to be about minus 2/3. And that is just going to look like noise in our pulsar timing data. Now, if we just looked at one pulsar, we would have no hope of distinguishing noise due to gravitational waves from noise due to like lots of other things in the data. Fortunately, we know that gravitational waves will be correlated among the pulsars, and they'll be correlated in a very special way. And this is what the correlation is expected to look like. This is the Hellings and Downs curve derived back in 1983. For pulsars that are in the same direction of the sky, we expect a positive correlation in the residuals at around 90 degrees. Because of this quadrupolar nature of gravitational waves, we expect an anti-correlation, and back at 180, we expect a correlation again. And so gravitational waves are really the only thing that will cause this quadrupolar signature in pulsar timing residuals. If we had a mistake like the clock at an observatory was off, that would be bad, but there'd be no angular correlation. If we had an ephemeris error, like we had the mass of Jupiter wrong, for instance, that would cause a spatial correlation actually, but it would be dipolar. It would not be quadrupolar. So this is a very exciting thing to look for in our data because it's a very specific signature of gravitational waves. Now, I don't have time to go into all these things at all, but I just wanted to show this table to point out that, of course, we have lots of other sources of noise in our data. There are other things in our data aside from gravitational waves that aren't deterministic, like those things in the timing model, right? Like pulsars aren't perfect rotators. Pulses can jitter back and forth. There can be scattering in the interstellar medium. Ephemeries for planets could be wrong. We could have clockers, but gravitational waves have a very special signature that does not, that's not the same as all these other things, right? So we can distinguish them easily, semi-easily. I'll show that in a couple slides, but we can distinguish them from these other things because they're the only signature that's correlated in space and quadrupolar, even though they have some qualities in common with these other noise sources. So of course we do that through a large Bayesian analysis where we fit for all the effects in our data. And we do that on about 80 millisecond pulsars. And so up until last year, we were observing roughly 80 of these millisecond pulsars at weekly to monthly cadences using primarily two telescopes, the Arecibo Observatory in Puerto Rico, the Green Bank Telescope here in West Virginia. And we have a small program on the VLA in New Mexico. This shows the sky distribution of our pulsars. We can't detect pulsars or observe pulsars at low declinations because we can't see them with these North American telescopes. Of course, as I'm sure you've all heard, we lost Arecibo last year, which was just awful and tragic personally and for our experiment. We're right now trying to supplement our program with other telescope data to try to compensate at least a little bit for the loss of Arecibo. We're adding data from CHIME. And this is amazing because CHIME observes pulsars every single day at lower frequencies than we currently observe. So this will really be a valuable addition to our data set. It's not as sensitive as Arecibo though, so it can't really replace it. And we just don't have as much time on the GBT as we need to observe all the Arecibo pulsars. It's also not big enough. So we've dropped about 20 pulsars. We're now observing only 60 millisecond pulsars. Fortunately though, we have a very long, very sensitive data set that we've built up over about 15 years. The way we work is we release these data sets every 2 years. And this figure here shows the growth of our data sets in time. The first one we published had 5 years of data, then we went to 9, 11, 12 and a half. This is what I'm going to talk about now. And right now we're working on the 15-year data set. And with each data set, we add more pulsars. Our cadence has increased. The different colors are different radio frequencies and telescopes. And you can grab our data. It's all public. You can do neat things with it aside from just pulsar timing. If you're interested in pulsar emission mechanisms, you can look at these extremely sensitive polarization profiles of our objects. You can look at some of the secondary science coming out, like proper motions. This is what the data will look like. You'll get a text file of times of arrival of pulsars, or of course you can get more complex data products. It's all available. It's all public. One big thing that we announced a couple years ago, which is probably a lot of interest to people in this group, is this very high mass neutron star that came out of measuring Shapiro delay to one of the pulsars in our array. And there's many more results like this that we expect to come out. I'm not going to spend any time on this because I'm running out of time. So let me just talk about our most recent analysis. So these are some images of our timing residuals from our 12 and a half year data set. That's our most recent data set. These aren't any three particularly special pulsars. They're just kind of to show you like what our data look like. You know, it's pretty messy. And what we do is cross-correlate the residuals of every pulsar with every other pulsar. And the reason I mention it's messy is to point out that, you know, occasionally people say, well, oh, there's these points that you can't explain with your timing model. There's this outlier here. There's a couple outliers down here, and that's absolutely true. These are probably due to interstellar medium effects that we're not properly accounting for. But the beauty of our correlation analysis is that we can tease out these kind of effects that are particular to one pulsar versus other effects that are correlated among all the pulsars in the array that might be due to gravitational waves. And so we search for all three of these signatures in our data, the stochastic background, continuous wave, burst sources, and we calculate probability density functions like this through this very sophisticated Bayesian analysis, which you can read about more in our recent papers. So this is a PDF on the gravitational wave amplitude. This is from our 11-year analysis. And the reason I'm showing this is just to show that when we looked at our 11-year data, we originally got results that looked like this, these dotted lines, and we were very excited. These were peaking at a particular gravitational wave amplitude, which is what we would expect for a detection. These SSEs are different solar system ephemeries. And what we found, though, is that when we changed the ephemeris, we got different answers. So these are different ephemeries from JPL. That's very bad. And what we realized with the 11-year analysis is that these ephemerides were not accurate enough to correct our data sufficiently to be able to search for gravitational waves. There were residual effects left over in the data. So there was still some correlation left in the data due to these incorrect ephemerides. So we developed a new code, it's called BaseFM, and it basically fits for the ephemeris at the same time as fitting for the gravitational waves. And now when we do that, we get PDFs that look more like upper limits. These two plots are basically the same. This right one shows Bayes factor, and this left one shows probability density, but they're basically the same. So this looks like an upper limit, this solid line now. So that was a very important effect. And even though we just got an upper limit, then we could say interesting astrophysical things. So we could place constraints on masses, the ratios between black hole masses and bulge masses, for instance, and say that some models, like this Corbin-Ho model, were very unlikely to be accurate, or else we would have already made a detection. So we're in a regime where we can place very robust astrophysical constraints, which is exciting. And these are our most recent results. So our most recent data set is the 12.5-year data set. And when we do our analysis on the 12.5-year data set, we find that we detect a common process very significantly. So it corresponds to an amplitude of about 2 times 10 to the minus 15. It's peaking at this very specific amplitude. It persists whether we use a fixed solar system ephemeris, this is the JPL one, this is a French one, or whether we use BaseFM. So this is very exciting. There's evidence for a very strong common red noise process among all the pulsars. However, we cannot yet distinguish the quadrupolar signature. We can't yet say this is definitely due to gravitational waves, because if you look at this Hellingsson-Downs curve, you can see the error bars have gone down between the 11 and 12.5-year data set, but we don't yet distinguish this quadrupolar signature significantly. There's a small Bayes factor that prefers the quadrupolar signature to the others, but it's not yet significant. So we can't say for sure these are gravitational waves. We expect in about couple years, a year or 2 years, in our next data set, which we're working on right now, we should see evidence at a signal to noise of about 4 to 7 of these quadrupolar correlations, if what we are seeing in the 12.5-year data set is actually gravitational waves. And this is very exciting. Once we can constrain the amplitude and the spectrum, we can really say things about galaxy formation and evolution, which is going to be extremely exciting. I think I'm
Maura, you have about 3 to 4 minutes left. Just to let you know. Thank you.
I'll go fast. So this is really exciting. These predictions are based on simulations of our data, projecting going forward. And even with the loss of Arecibo, which is tragic, we should get there very soon. So it's a very exciting time. Let me just talk very briefly about the other kinds of sources we're searching for. So we're also looking for individual sources of gravitational waves. This is our sky average sensitivity to these continuous wave or individual sources. There's not too much to say about this plot aside from it's getting better with time as we expect. So that's good news. This shows the direction dependence of our sensitivity. So this color bar here shows like how far we could detect a gravitational wave source, a billion mass gravitational wave binary with a particular frequency. You can see it looks very anisotropic. So in some directions of the sky, we can say there are no supermassive black hole binaries out to like 120 megaparsecs. In some directions, it's only to 20 megaparsecs. And the reason for this is that our best pulsars are all in this part of the sky. And we don't have a lot of good pulsars over here. So we're trying to add more pulsars in this part of the sky to kind of like even out our sensitivity. But it's very exciting. Like we can already say things like, in Virgo, we know there are no supermassive black hole binaries with masses greater than about 1 billion solar masses, or we would have seen them. And these numbers, these mass limits are going to get lower and lower, and the distances are going to get, further and further out with time. We've also done our first targeted gravitational wave source at an electromagnetic source. So very recently, we published a paper where we looked for the supermassive black hole that's purported to be at the core of 3C66b. And we use those electromagnetic parameters as priors, which makes us much more sensitive. This is the predicted mass, this orange line here, and this is our posterior distribution on the mass. We're not quite there yet. We can't rule out the predicted mass. This is our 95% confidence upper limit, but we should get there in a few years. So this is very exciting. We should either make a detection of this system or be able to tell the community that the electromagnetically inferred mass limit should be revised. And I'm just going to skip this. I'll just say simulations show that we expect a blind detection of one of these continuous wave sources within 10 years. I think the first detection, though, will be done based on an electromagnetic prior and may happen much sooner than that. Okay, finally, I just wanted to remind everyone that NANOGrav is not operating alone. We're part of a large international collaboration called the International Pulsar Timing Array. We're using telescopes all over the world to do this experiment. And this is a very exciting effort. By combining the data from all these telescopes worldwide, we should be able to build a much more sensitive data set than with NANOGrav alone. So this is really the way of the future, and we're putting a lot of effort into this international collaboration. I'll just leave this final slide up since I'm short on time. Thank you so much.
All right, thank you, Maura, for an excellent talk. We don't have any questions right now in the Q&A. If anybody would like to type one quickly, or please go ahead. In the meantime, perhaps since I rushed you so much, maybe if you'd like to go over, pick one particular area that you felt like you had to skip over that you would have really liked to talk about, and tell us that for a couple minutes while we see if any questions come in.
I mean, sure, I can go back. I think there was just one slide that I totally didn't talk about.
Right.
And let me just point out that, one thing that we get sometimes is like, why are you doing this experiment? You're just going to get a number. You're just going to get an amplitude and a frequency. And what's that going to tell us? Well, at first, that's what we're going to get. But in time, in 5 to 10 years, we're going to be doing true multi-messenger astronomy, where we are able to observe gravitational wave sources, galaxy mergers that are also observed with electromagnetic observatories. And that's going to give us a wealth of information about the astrophysics of these mergers. One thing that we've done is looked at galaxies detected by other surveys. So this particular study looks at galaxies detected by 2MASS and runs a bunch of simulations based on those, the mass and redshift distribution to see in how many cases they're detectable. Right now with our current PTA, and this is actually old, this is the 11-year, it hasn't been redone for most data sets, a small number are detectable. But these show these simulated galaxies, the strains of these simulated galaxies. In this particular realization, here's the brightest one, just above our sensitivity curve. If we happen to be looking, it happens to be in the most sensitive direction of the sky. Sorry, I'm trying to rush. But we expect a blind detection based on these kind of simulations in 10 years. And so I guess the point I just make is that this is real multi-messenger astrophysics. And that's what we're aiming to get at within the next, like 5 to 10 years past the stochastic background detection.
Okay, excellent. We have some questions that have been pouring in. Let me ask the first one. What are the timescales or milestones we could expect for IPTA?
That's a great question. So the IPTA has released 2 data releases so far. The gravitational wave analysis on that second release is going on right now. It'll come out soon. It will not be more sensitive than the NANOGrav data though, because the analysis has taken quite a long time. So NANOGrav has actually surpassed the sensitivity of that IPTA data release. The next one is data release 3. We're hoping that will include our 15-year data set and other up-to-date data sets. And that data set should be much more sensitive than the data sets of any of the individual PTAs. So that one should be the one to provide, a really definitive detection. And then we hope in time, 2 or 3 years down the line, I think that one might come out. I'm just guesstimating, but I think about, 2 years or so. The IPTA data set, I hope, will always be more sensitive than our data set, which hasn't been the case so far, just due to the complications of combining data from all these telescopes taken in different ways and different people and collaborations.
All right, thank you. A second question, could you comment more on NANOGrav's position for electromagnetic signals of pulsars? Is it competitive with other observational tools?
Signatures of electromagnetic signals from pulsars?
It says NANOGrav's position for electromagnetic signals of pulsars. Is it competitive with other observational tools?
I'm not sure what that means exactly.
Okay.
I don't know if
we can maybe revisit that one in a coffee break or
yeah,
if you'd like, because there is one other question and we have about a minute left. So let me just go on. Are there any plausible early universe stochastic backgrounds which are above the stochastic background from supermassive binaries?
That's a great question. I didn't talk about that because I just didn't have time, but there are 2 other stochastic background sources that we could detect. One of them is the signature from early universe inflation. The other one's due to cosmic strings. Both of those signatures are expected to have a red spectrum, similar to that from supermassive black hole binaries, but not identical. The spectral indices should be different. There are models which predict that this early universe background should be detected in our data. They're kind of outliers. Most models predict it should be at a much lower level than the supermassive black hole binary, but we don't really know. So it's quite possible. Well, I think it's unlikely. I think we'll see the supermassive black hole binary first based on all the different predictions. But it's possible that with time we'll be able to tease out a signature from early universe inflation and supermassive black hole binaries and possibly cosmic strings due to their different spectral indices. And a graduate student of mine is actually working on this right now by simulating these different backgrounds with different amplitudes and trying to figure out like when we'll be able to distinguish more than one background contribution. And it's probably not in our 15-year data set, but it could be in our 17-year data set.
All right. Thank you very much, Maura. Thank you for your excellent talk.